All right, folks, welcome to Wednesday's lecture. I guess you can think of it that way. We're going to wrap up some fronts here, and then we'll make some additional videos with the idea that this is going to encapsulate both Wednesday and Friday's lectures this week. Please, again, pay attention to the other things such as the quiz that needs to be taken at a certain time on Friday. And of course, assuming you're watching this prior to lab on Thursday, remember that both assignment number 2 as well as your lab on force balances is also due at the end of lab this week. So you should be familiar with the slide that's up on the screen right now, the idea that we're looking at cold frontal boundaries, recalling that when we talk about fronts, we're talking about the type of air that is displacing another air mass. So here the continental polar driving in from the northwest, displacing that maritime tropical air. We draw these little pips, or here blue triangles showing the direction the front is moving. So here a south-southeast direction across Tennessee and Arkansas. And the number of clues that we talked about on an earlier slide to indicate where we might position a frontal boundary. And so that's going to be a lot of what we deal with as we work through this section. We looked at a couple of these schematics from a three-dimensional perspective, recalling that even though we're typically going to look at frontal boundaries on a screen or a map or something like that, that they actually are three-dimensional in nature. And so there's a lot going on here, to be honest, and it is going to take a little while to understand the nuances and differences between the fronts. The critical information is what you really need. For instance, again, remembering that the cold front is going to be where cold air is replacing warm air. When we see cold fronts, we oftentimes find some lifting motion or rising motion that's associated with the lift in association with the cold front itself. So here in this schematic with an overlay of radar, we see a front driving across Kentucky and Tennessee. Interestingly enough, not far away from where the previous slide had a front. And now we overlay it with some radar imagery, and you can see these brighter echoes across Tennessee, the reds and yellows, indicating where we would have some type of thunderstorm activity. This is that warm, moist air that's being lifted up because of the cold frontal boundary. Doesn't mean that we only see precipitation on one side of the boundary, and go back to the previous schematics if you need to hammer those points home. But regardless, we're lifting up this air mass, this less dense warm air, by this colder, denser air mass, replacing it, here firmly entrenched across Illinois and Missouri, and that is potentially going to lead to showers, rain, and thunderstorms at times. Most of the time when we discuss cold fronts, we're thinking about a big low pressure system moving across the country and a cold front that kind of wraps in behind our low pressure. And this is going to become more clear as we work our way into mid-latitude cyclones here on the next slide series. Here we look at a different kind of backdoor cold front where we have this maritime polar, this cold but kind of clammy and moist air mass here moving. And here it's moving differently than we might expect traditional fronts. Recalling back to global circulation, we live here in the mid-latitudes in a belt called the Westerlies. The idea that our weather systems generally move from west to east across the United States. In this example, we actually have a boundary that's moving from east to west, pushing in because of that dense, cool maritime polar air is able to effectively take over some of that warm, moist air that would have been in place over areas such as New York, and areas like New York City and Connecticut in this example. So here we got a location in Connecticut with that east-northeast flow, cold and moist, and out ahead of it there in Pennsylvania, much warmer and more moisture in the air, but definitely not nearly the 100% relative humidity we're seeing behind this frontal boundary. As I have in this little inset box, this is not exactly how things work in Chicagoland, so if you're from anywhere around the city, you probably have heard the weather forecast and they'll say and cooler by the lake. Or they may say temperatures cooling off in the afternoon by the lake. And the idea is that in summertime, we're going to have lake temperatures that are cooler than, well, what the temperatures get to be over land. And this goes back all the way to the ideas of specific heat. And so as we get that warmer temperature inland, that less dense air over the land, and then the more dense air that's firmly entrenched over the lake can kind of push inland. And so this is why we can find cooler temperatures near Lake Michigan on a number of summer days in particular. These boundaries will make it down to Valpo occasionally, but we're about 10 to 12 miles off the lake here in Valpo, so it doesn't make it that far inland all the time. Moving on to our next type of front, the warm frontal boundary. Well, a lot of what we'll talk about here with the warm front is kind of a cold front in reverse. Here the warm air is doing the replacing. It is effectively moving out the colder air. And so we'll see on a 3D schematic how this works. The idea here is that you have this strong advection of air in this schematic here from the southwest, pushing the warm air north and eastward in this example. The maritime tropical air mass, or at times a continental tropical air mass, is effectively replacing a continental polar air mass. Again, reversing what we discussed with the cold frontal boundary. Here you see instead of a blue line, we depict it with a red line, and instead of blue triangles, we have red semicircles. However, we are the same in the sense that the semicircles are pointing in the direction that the frontal boundary is moving. So although there's no states to really see below this map, we would have this boundary draped in this general area, and it would be lifting off towards this direction over time. That's the idea of how a warm frontal boundary would proceed. Understanding that you don't always see these in color, we do keep triangles for cold fronts and semicircles for a warm front. In fairness, I can't exactly tell you why that depiction came about to be. And so again, this warm air is going to always be less dense than cold air. It's still going to make an advancement, but oftentimes our warm fronts are not going to move as quickly as our cold fronts will. This warm air also is forced to rise up and over the existing cold air. As a result, the lifting mechanism associated with the warm frontal boundary is going to bring that warm air and cool it to temperatures where we can get clouds and precipitation, and we oftentimes will find widespread precipitation associated with a warm frontal boundary. In this schematic, you can see that they're depicting a number of different types of precipitation. Temperatures south and west of the boundary, mid-50s. But as you work your way to the other side of the boundary, we quickly see areas here that are saturated in the upper 30s, followed by areas very close to the freezing point, and then areas here that are actually below freezing. And so this may be sometimes where we do see a lot of mixed precipitation, potentially even icy weather, as is shown by these little squiggly lines here in this pink area, sleet and freezing rain. And then depending on how things hang on, you can get some areas that will experience widespread snowfall. And so in this schematic, we actually have the frontal boundary moving the opposite direction of what we saw earlier with the cold front. Here, it's moving from the right side of your screen towards the left side of the screen. Again, don't get too caught up in the P's and P1, P2, P3. That's just pressure isobar type things. But what you can see is as this warm air at the surface is moving from the right side to the left side, as it is aloft, it's being forced to rise up and over this existing dome of cold air. Again, remembering that this air mass that's moving in is typically going to be a maritime tropical air mass. It's going to be warm and moist, and it's effectively butting up against an area that's cold and, to a certain extent, drier. As this air is lifted upward above that cold dome of air, you can see a number of different little two-letter identifiers for stratus, nimbostratus, altostratus, cirrostratus, cirrus, harkening back to when we had our section on precipitation and clouds. Regardless, this will oftentimes mean that there's a widespread area of precipitation, especially on the cold side of a warm frontal boundary. And so a couple other examples here. Now we have our boundary moving from the left side of the schematic towards the right side of the schematic. And effectively these are the same image, just trying to depict different things with regards to clouds and precip versus things related to temperature profiles and winds throughout the depth of the atmosphere. Again, your warm air, less dense, is forced upward and over the cold dome. Here again we see the widespread difference in precipitation that may be expected. Mind you, if you're in a very cold area, it may all be snow, and if you have a warm frontal boundary here in Valpo in the middle of July, don't expect to see any sleet or snow at all. It's simply going to be rain. You can also see how winds may change and maybe a southeasterly direction changing to a southwesterly or westerly direction with height. We'll talk about this idea of wind shear as we get later on into the semester and deal with severe storms and tornadoes. But there's a lot going on with the warm frontal boundary, including this wide expanse of precipitation that may have some type of mixed precipitation event depending on the season. And so sometimes our boundaries slow down or even stall out. And so instead of a cold front or warm front, we're going to depict this kind of as a hybrid of both. And we'll refer to this as a stationary front or stationary boundary. Stationary basically means that it has minimal movement. It may be meandering a little bit to the north or south in this example, but it's not having any type of significant movement in either direction. In reality, even though stationary would mean it's not moving at all, technically speaking, these boundaries can move up to about 5 miles an hour, which, let's be fair, is pretty darn slow. The weather associated with a stationary front, though, is quite similar to that of a warm front. Here, that warm air mass to the south, which we can see in this schematic, the little arrows are trying to show that the flow is kind of parallel to the boundary. There's no big cross-frontal push of either one of these air masses, and that's why the boundary would not be moving very much. Regardless, this maritime tropical air mass is going to be forced up and over this existing entrenched cold dome north of the boundary, and that's going to result in the expansive precip being primarily on the cold side of the stationary boundary. As it rises, we may see areas of rain, freezing rain, sleet, ice pellets, and even snow with this example. How do we depict or how do we draw a stationary boundary? We're going to find alternating red and blue line with blue triangles and semicircles. Basically, take a warm front and a cold front, lay them on top of each other, and just change the color every so often. It is important to note that, again, if the warm air were advancing, it would be advancing to the north, and so we draw the red semicircles in the direction the warm air would be advancing. And conversely, we see the blue triangles in the direction that the cold air would be advancing. Now, if for some reason the stationary boundary starts to move notably in either direction, forecasters or computer programs should change it to be a cold front or a warm front to illustrate the fact that it does have some type of motion in a given direction. When we look at the 3D schematic of a stationary boundary, one thing you'll notice it looks really similar to that of a warm front. The one difference being you see the flow at the surface is generally parallel again to the boundary, minimal cross-boundary flow. We see a little bit of a different feel to these pressure lines at the surface, but as you look on the plane or the vertical side of things, really very similar in terms of the expanse of rain and snow, and not necessarily any difference really in how the warm air is gliding up above the cold air mass. We transition a little bit here to talk about a special type of boundary. And don't worry, we're almost done with this section. A few slides, we'll be done within about 5 minutes. Here we talk about what's known as a dry line. A dry line is a special type of boundary, and as you can see in the top bullet, not a front in the truest sense. It's not a front in the sense that it's not a big difference in terms of the air mass tendency, or the type I should say. We still have tropical air on both sides of a dry line. It's effectively a moisture discontinuity. Continental tropical air, which is much drier, is replacing moist maritime tropical air. And so in this top schematic, you can see temperatures behind your dry line well into the 90s and even the hundreds here across West Texas. East, it's still darn hot. It's in the upper 80s to low 90s, but the big difference here is in the dew points. You can see the dew points in the mid 60s to upper 60s to even low 70s here to the east side of your dry line versus 36, 24, much drier conditions. And so this is what we mean by a moisture discontinuity. And this is going to be a type of boundary that does not necessarily exist through much of the United States. We're going to primarily find dry lines across the plains and find them during the summertime months. And so you can even see in the bullets, Texas, Oklahoma, Kansas, maybe up into Nebraska at times. Once in a while, we can get these to move towards Missouri and Arkansas and Louisiana. Very rarely would a dry line, a pure dry line, make it all the way to someplace like Valparaiso, Indiana. Dry lines are interesting in the sense that they move east during the day and then they retrograde back towards the west at night. They move by what's known as mixing, and in fairness, that's not something that's particularly critical to this class. But when we talked about warm fronts and cold fronts, we expect them to generally keep moving in the same direction, whether it's day or night, and if anything, just to slow down and turn into a stationary type boundary. But these can basically evolve from where you see it here in this lower schematic, maybe move into central Texas, and then reset back here in the next morning. We see this depicted by a brown line with hollow brown semicircles, and then sometimes they're filled brown semicircles. The reason we bring up the dry line is the dry line is still a boundary that can produce lift. And lift, as we'll find later on, is a critical component or part of the recipe, shall we say, for severe weather. And so when we focus on a dry line, and in this example, this is real data here, not all the different schematics that we show. We got temperatures of 79 over 67 east of the dry line, 85 over 11 to the west of the dry line. And even though this is Texas, and yes, that's not an inconsequential distance, that's still not that far to see differences in dew points of, well, over 50 degrees. And so when we see examples like this, we're really going to focus in this area just ahead of the dry line where we have enough moisture as one of the ingredients we also need for thunderstorms and severe weather, but this added lift from the dry line. We'll talk about other things later on like shear, spin in the atmosphere that can also make some of our thunderstorms turn severe in nature. And so we conclude our discussion of boundaries with the occluded front. When we talked about cold fronts and warm fronts, I hinted upon the fact that cold fronts, because of that driving, dense cold air, often move faster than a warm front. And so when we talk about a occluded front, we're effectively suggesting that that warm air catches up to the existing warm front. And so in this example, we'll see this even more as we work our way into mid-latitude cyclones. You see your low pressure here. I guess if I look at this map, maybe somewhere like South Dakota, North Dakota area. And normally we'd see a warm front extending off to the east, a cold front trailing to the southwest. But over time, that air mass, the cold air mass, catches up to the warm air mass. And so we turn it into what's known as an occluded front. Go embrace your inner kindergartner, find some red crayons and some blue crayons and scribble on a piece of paper and you'll generate the color purple. And so we see here a purple line with purple triangles and semicircles. The idea that here the warm front is moving off to the northeast, cold front is driving towards the southeast, and so in general the spin around a low here in the northern hemisphere is going to be counterclockwise, and so this boundary is moving off to the east as well. And so that's the different characteristics that we see here. Bottom bullet, this is that cold air that's wrapped fully around your cyclone. And so if you do dive into the book a little bit, I know, you'll see that the book will talk about cold and warm occlusions. And we're going to focus on the cold variety of the occlusion. So again, what you'll find in this example is the area out ahead of your occluded front and also therefore ahead of your warm front is going to be cold in nature as opposed to air that's much colder coming in behind the cyclone. Colder air is replacing cold air effectively with a cold occlusion. And so this is the general schematic of how this would work. And so we conclude with this slide, the idea of the frontal occlusion. And so this is kind of an odd schematic. I don't make these, and for that I do apologize. Basically, you start off here with this 3D type scenario where you have the cold front pressing in towards the warm front. You have this small area in between where the air is warm because the warm air is pushing out the cold air, but this even colder air mass is pushing in more quickly. And so this area effectively gets overtaken and it pinches off the area at the surface more quickly than it does areas that are aloft. And so we see that in this general example of A to B to C down here. And what you're looking at are these three cross sections. In A, we're kind of looking down here where we have cold, very cold air, a little bit of a warm sector followed by the cold air out ahead of your warm front. B, we're working our way right through this little triple point area where all three boundaries meet one another. And this is, again, kind of where the occlusion is found at the surface. And then if we work our way up to C, where we have no semblance of anything at the surface regarding warm air, we simply see very cold air pushing in behind, cold air out ahead, and all the warm air is trapped far aloft. We'll talk a little bit later on about the fact that once a system occludes, this effectively means that the mid-latitude cyclone is going to weaken. There are times in which our triple point, as I say, where the three come together, can start to form a new cyclone, but still, occlusions are a critical part of the mid-latitude cyclone life cycle, so to speak. That's all for our frontal boundary section. Definitely take a little bit of a break, and there will be other videos again to encompass class both Wednesday and Thursday and Friday of this week. Take care. Stay healthy.